So, good morning, everyone. My name is Tomé Albuquerque, and today I will present my work with Sajid Ali. It's on the task 3, Integrated Diagnosis, and the work is entitled Multimodal Prognosis of Lung Cancer Risk, a Preliminary Study. If you want to see the code, you can check this QR code, and then you go to our GitHub page. So this is the agenda for today. First, I will try to do an overview of the task. Then I will try to understanding the data set, the data formulation that we have done to train the models, the methods that we use, the results, and finally some final remarks and future directions. So starting with the overview of the task. So we have a lot of unanswered questions that we try to answer in this work. Basically, why we must use multimodal data as input for the models, what can this benefit the model, how to combine them. So there is any advantage of do that in the performance of the model and so on. And then this is the starting point for this work. So regarding the data, we have one data set that contains 3 different input sources, like blood values, where we have 19 features, the radiology exam that we have 8 features, and the temperature of the patients. So beyond that, we have the output levels in risk 1, risk 2, and risk 3. So for the training, we have 1,000 samples. For the validation samples, we have 250, and for the testing, we have also 250. So to address this problem, we try to start with a baseline model where we use the mean values of blood values and the last value of radiology and the mean temperature. Basically, we need to do some data encoding because we have the risk in this type of encoding, and then we move on to this type. Basically, in the second approach, we use the mean values and also the standard deviation values to give us a range of values that could be useful for the models. The first approach that I was talking about, it was multimodal, but we also want to know what's the predictions only using unimodal input. So we also do some experiments using only one type of each data set that we use the blood values in the first approach. In the second, only the radiology values, and then in the third, only the temperature. So for the methods, we use a very well-known model, which is called XGBoost, and it's based on a decision tree. And here you have the hyperparameters if you want to test and reproduce our results. So basically, using the multimodal, the results for the multimodal model, in the multi-class, we have a very low accuracy. And we also printed the SHAP value to see what's the influence of the each feature in the model decision. As you can see, the urea is the most influence in this SHAP graph. And then after we had the standard deviation features, we can see there is a shift. Basically, the standard deviation of urea is more important than the mean value of urea, which is interesting because now we have a range of values and we see that they have more impact in the model than using only the mean. Then we try also just a quick experiment, just try to classifying no risk or risk of lung cancer. And we have an accuracy of 60%. And then we try to do the same and add the standard deviation values, and then we have an improvement of like 11%. After that, we try to compare the unimodal approaches versus the multimodal, and then we can see clearly that there is an advantage of using a multimodal inputs in the model in basically in three different metrics. It wants only the unimodal, and in this case the best unimodal model that we have, it was using the blood features, and basically it only wants in precision, but it's very close to the multimodal. As you can see, there is an evidence that we must use multimodal data. However, there is a lot of room to improve and so on, because this is very low results, but I think there is an improvement. As final remarks and some future directions, we can see that XGBoost can be a good choice for this type of data. It's tabular data, and XGBoost it's proof that it's very good in literature for this type of data. We can also see that the addition of the standard deviation will give us a range of time features, improve the model performance, and as future goes, because we don't have much time during the weekend, we want to compute other time domain statistical features like the variance, like the maximum quartile, like another type of time domain features that can improve the model performance. And we also think about because in these data sets there are a lot of missing data, and I think it's important, if it's possible, to test some methods to fulfill the missing data to improve the models. And I think that's it. Thank you all. Thank you for this opportunity to participate in this hackathon, and congratulations to the organization. Thank you for your time.